spin, ket space and ordinary space. Before we begin, let's just note, for later, that any unit vector v can be expressed as a linear combination of a component along the theta direction and another component orthogonal to that. It is simultaneously possible to express v as the sum of cos theta 1 plus sin theta 1 or as the sum of cos theta 2 plus sin theta 2. But it is not possible to express v as the sum of cos theta 1 plus sin theta 1 plus cos theta 2 plus sin theta 2. That is, v has components in all those directions, but it is neither the sum of all of them, nor can it point in more than one direction at a time. Anyway, let's get on with it. Suppose there are three possible locations for a ball along the x-axis. Suppose it could be at location x equals -2, at location x equals 2, or at location x equals 6. It might have a higher probability of being at some of those locations than at others, but whatever the probabilities it has of being at the various possible locations, those probabilities must sum to 1. Or to 100% if counted in percentages. We could represent this on a straight line as shown, which is perhaps the most obvious way of representing it. But we could also represent it on a unit sphere, using different orthogonal directions to represent the different possible x positions. The projections of vector r onto the green, red and blue position vectors then represent the probabilities of the ball being found at positions x equals -2, x equals 2, and x equals 6 respectively. Notice that the sum of the squares of the projections equals 1. Notice also that if the vector r lies along any of the three specified unit vectors, it has then no projection onto any of the other unit vectors, since r is then orthogonal to all those other unit vectors. This is how, in quantum mechanics, orthogonality is used to represent mutual exclusivity. For example, if the ball is at x equals 2, it is not at x equals -2. And thus, when r lies along the x equals 2 vector, the square of its projection onto the x equals 2 vector, which is the probability of the ball being found at location x equals 2, is equal to 1, and r has zero projection onto any of the other orthogonal vectors. It is then said to be in an eigenstate. Notice also, in this representation, the minus of the x equals 2 vector is not the same thing as the x equals -2 vector. Although it cannot be drawn, this representation generalizes to infinite dimensions, which are not infinite dimensions in the spatial sense, but simply a notional representation of the infinite number of possible mutually exclusive locations along the x-axis. A similar method is used to represent any other measurable quantity, for example momentum. There are complex numbers involved as well, but the point being made here is simply that orthogonality is used to represent mutual exclusivity instead of meaning at 90 degrees to, as the word orthogonal is normally used in geometry. For example, the possible measured x eigenstates of a spin can be along the plus x direction or along the minus x direction. But instead of being represented as two mutually exclusive possible outcomes along the plus x and minus x directions in ordinary space, these outcomes, being mutually exclusive, are represented as two mutually orthogonal x-ket vectors in a two-dimensional z plus z minus complex vector space, even though the plus x direction and the minus x direction in real space are anti-parallel. Because a spin in a z eigenstate, when measured in the x direction, will be found to be either fully along the plus x direction or fully along the minus x direction, the z-ket is expressed as a simultaneous linear combination of the plus x-ket vector and the minus x-ket vector. However, in reality, spins are actually measured in real space, not in the abstract mathematical vector space used to represent them. Consider real space. For illustration purposes, one single zig and one single zag is being used here to represent an infinity of infinitesimal zigzags. Each infinitesimal zig of which represents r plus for an infinitesimal duration. And each infinitesimal zag of which represents r minus for an infinitesimal duration. Where r plus equals z plus a unit positive x and r minus equals z plus a unit negative x. Notice that in actual space the relation of the resultant vector r over 2 to z is the same as that of 1 over root 2 times the x ket to the z ket in the complex vector space. In actual space, the x component of spin is never simultaneously both plus along x and minus along x, for that would simply result in an x component equal to 0. Only the x-ket vectors in the complex vector space can be said to be simultaneously acting to produce the z-ket vector because the plus and minus x-ket vectors are orthogonal to each other. This difference between the unit x-ket vectors in the complex vector space and the unit x vectors in real space is almost never mentioned in conversations on this topic, but it is of crucial significance. Notice also that r plus and r minus are never simultaneously the case, since in actual space, x plus and x minus spin eigenvectors are never simultaneously the case. The projection of the real space z eigenvector onto the real space x eigenvector is 0, since cos pi over 2 equals 0, in other words, a z spin eigenstate has a plus x component, cos squared pi over 4 of the time, and a minus x component, sine squared pi over 4 of the time. The representation of quantum spin by means of vectors in a two-dimensional complex vector space works as a mathematical modeling of spin. But the reason such a representation of spin works as a mathematical representation at all is because, with respect to the real space z and x directions, there really is, at any one time, either a resultant r plus, which is a combination of a unit z spin and a positive unit x spin, or a resultant r minus, which is a combination of a unit z spin and a negative unit x spin. Notice that both the green and the blue lines in the 3D z plus z minus t space have identical projection onto the 2D z plus z minus plane as the parallelogram formed by the x plus and x minus ket vectors. By pretending that time does not exist in the real universe, ignoring the time dimension altogether, we can obscure this distinction. Conversely, to make this distinction apparent, we need to also include the dimension of time as a time axis on the two-dimensional z plus z minus plane. The only reason the two blue lines can correctly represent spin components at all is because in reality, there exists the two green lines to give rise to the necessary projected parallelogram in the z plus z minus plane. Representing spin as points on the Bloch sphere provides a method of calculating spins, but it does so at the expense of clarity. The reason a z spin eigenstate gives either a plus x or a minus x spin eigenstate when it is measured in the x direction is that z is in fact a sequential linear combination of r plus over 2 and r minus over 2 in real space. And the reason the 2D complex vector space representation of spin correctly models spin is precisely because r plus over 2 has the same relation to z in real space as 1 over root 2 times the x minus ket has to the z plus ket in the complex vector space, and r minus over 2 has the same relation to z in real space as 1 over root 2 times the x plus ket has to z plus ket in the complex vector space. The two simultaneous blue world lines have the exact same projection onto the z plus z minus plane as the two sequential green world lines have onto the zx plane. And a point takes exactly the same amount of time to go from 0, 0, 0 to 1, 0, 1 in the z plus z minus t space as a point takes to go from 0, 0, 0 to 1, 0, 1 in the zxt space. The blue and green representations have the exact same projection onto the plane and therefore produce the same z eigenvector. It is worth emphasizing again that whilst the spin is in a z eigenstate, it is not the unit x plus and x minus vectors in ordinary space, but rather it is the x plus and x minus ket vectors in the 2D complex vector space, which are simultaneously the case and which combine in a simultaneous linear combination to produce the z eigenket. The relation of the complex space to real space is a relation of simultaneous linear combination to sequential linear combination. In other words, the x-kets in the complex space do not map to the positive and negative real space x directions, but rather map to real space r plus and r minus vectors that are sequentially the case and form the z eigenvector by a sequential linear combination. The two representations sharing the same projected parallelogram with respect to the measured z-spin eigenvector